Okay, welcome my dear students. Last class we discussed about the matrix associated with the linear map, and this class we have to find how to find a rank and nullity of a matrix. So we in the last class we know that we said that every m by n matrix A corresponding to a unique linear transformation from Vn to Mn, or you can say that Rn to Rm, and we have agreed to use the basis of the both the spaces, means basis of a Vn and basis of a Vm. So this case we can say how to find this. So means the range, kernel, rank, and nullity of a matrix are defined as a range, kernel, rank, and nullity of a linear transformation. One thing is very basic clearly is this: we know that in the last class, that means we have a matrix is there corresponding to this matrix. We find a unique linear transformation from the if we have a m by n matrix, so Vn to Vm. So clearly we have to find a linear transformation, and then you know that how to find a linear transformation. We know that how to find the rank, nullity, and kernel of a linear transformation. Means rank is nothing but is equal to image of a linear transformation. And also we can say that nullity is nothing but is equal to, we show that if the all the map is mapped Tx is equal to 0 of this basis, and the dimension basis of a range of A is called the we have a rank, and the basis of the kernel of this is called the nullity, or we can say that nullity of this matrix. So this for a matrix case is also because every matrix we can corresponding to a matrix we find a unique linear transformation. So range, kernel, rank, nullity of a matrix are defined as a range, kernel, rank, and nullity of a linear transformation. Okay, so I just take what is the range of A. That means A is nothing but is equal to A. If we have A is Vn to Vm be the set of all the vectors of the form Ax belongs to the A to the power m, and x is the element of a, we have a V. This means we have a, if we have a, clearly we have a map from Vn vector space dimension n to vector space dimension m, and then element of a, this is the form of a x. This x is the element of a V of n, and then clearly we can say that this is the element of a n, then this is maps to clearly element of a, this is the form of nothing but is equal to Ax types, this is the element of a Vm. So this means, or where A is what? A is nothing but is equal to, we have a matrix. So A is equal to, we have a alpha ij is a set of all the column vectors that are a linearly combination of the column vectors of A. So alpha ij is the set of all columns of a vectors that are, because you know that we just write a with this when we calculating the matrix associated, we have a matrix is given, and then we have a basis C, B and C is given. Then we have every element of this column vectors of this can be written as a finite linear combination of the elements of this C, and then we can say that this this element of this combination of this can be written as a linear combination of the elements of this B. So this way we can construct a linear transformation. The similar fashion we can just say that we have a set of all the column vectors of this are a linear combination of the column vectors of A. For this, the range of A is the set of all the vectors of the form of this, where for A is equal to alpha ij is the set of a column vectors of the form, means this is the alpha ij means column vector of the alpha 1 x1 plus alpha 1 2 x2, this is and so on. This is the, then this we have a like this, we have to write all these things, we have to calculating into this form. If we take a columns vectors of this form, this means this is the one of the columns of this, and this is the this way we can say that if this is of the columns of this, we have to set of all of the form of this form. Now this can be written in the form of a x1 we can write as x1, we can write as a alpha 1 1, alpha 2 1, and so on alpha m1, and plus we can write x2 is the same of the column, we can say that alpha 1 2, alpha 2 2, and alpha of m2 m. In the similar fashion we go up to nth, and now you see this is x1 x2 xn are the element basis of this arn, as this means we can say that this is plus x to the xn, we can write as the column is equal to L1n up to m n, and this x1, x2, xn are the linear combination of the bases of a Rn. So this means these are the columns are, if these columns are called the range of a, this is nothing but is equal to, so we can say the range of A is nothing but is equal to the alpha 1 1 to alpha m1 transpose and so on. This is the range of A. We can write in the form, if all these vectors are linearly independent, then this form a basis. If it is a form as a basis, the number of element in the range of basis of a range of A is called the rank of this thing. So this is the clearly we have to know that. Okay, this means I just said that written in this form, and this clearly this is just is a linear combination of the column vectors of A. Obviously, column vectors A are the vectors of Rn, and thus we have the following result. We can say that the range of an m by n matrix is the span of its column vector. This means range is nothing but is equal to range of A is nothing but is equal to, we can say that span of the column vectors alpha 1 1 to alpha m1 transpose, then we have a alpha 1 2 alpha 2 2 up to alpha m2 ka transpose and so on. We have a alpha 1n alpha 2n up to alpha mn ka transpose. Span of this is equal to this. And now if this span is linearly independent, then we can say that the rank simply. The rank of a matrix A is the dimension of the range of A, the span of the column vectors A. This shows that the rank of A is the maximum number of linearly independent column vectors of A. So that means we can say that clearly we can find the, if we have any matrix is given, this matrix rank we find what is the range of this range of such a matrix is nothing but is equal to, we can write the span of this column vectors, and the rank of this matrix is simply if these column span are the linear independent, then we can say that is a number of element in the basis of is called is the rank of a such matrix there. Okay, so let us start with one example. You just take this is the then the range of A, this in this case we can say the range of A is nothing but is equal to, we can say that span of, by the definition we have a 3 2 1 0 ka transpose, we have a 1 minus 1 1 ka transpose, then we have a 2 0 1 2 ka transpose. Now this is the range of this matrix is equal to this form. Now you can see clearly these three vectors, all three vectors are linearly independent. If these three vectors are linearly independent, means we can say that because this is second position is 0, now second position is non-zero terms here, and then if we take any multiplication of this is not equal to 0. So we can say that clearly we can say these three vectors are linearly independent. If they are linearly independent, then we can say that the rank of A is equal to, we have a 3. Okay, so this means this is 3 this. Now we have a rank of A is equal to 0 since these three vectors listed are linearly independent. If these all the vectors are listed here is linearly independent, then we can say that this clearly this is a rank of this matrix. Okay, now we try to find out what about this. So we have a range of A is equal to, we have a, you can write the span of the, we have a 3 0 1 transpose, 1 2 minus 1 transpose, 4 2 0 transpose, 0 0 0 transpose. And now you see clearly this set is linearly independent because 0 vector is already is there. So we can write this is a span of nothing but is equal to, we have a 3 0 1 transpose, we have a 1 2 minus 1 transpose, we have a 4 2 and you have a 0 ka transpose. So we can just say that this. Now check is we have a 4 2 0. Now we check is these three vectors are linearly independent or not. Now we check, you have a 4 2 0 can be written as a 1 into, you have a 3 0 1 plus 1 into, you have a 1 2 minus 1. So this means these three vectors are clearly linearly dependent. If these three vectors are clearly dependent, then we can write the span of this is nothing but is equal to 3 0 1 ka transpose, and you have a 1 2 minus 1 ka transpose. Then the span of a range of A is equal to clearly is this form. And now because you just check these two vectors are clearly independent because none of them is a scalar multiple of a other. So this means this is linear independent. So this is the span of this. Now we can say that this rank of this matrix A is equal to, we have a 2. So we have to just say that it's in a span of this as only we have 2 elements. So this means we can say that in this case we have a clearly this set as containing of a rank of this matrix is equal to we have a 2. Okay, so now we just take into this form. Okay, this is clearly A has a rank 2 because these two vectors are linearly independent. Now next is definition is about the kernel. The kernel of a is the set of all the vector x belongs to the Vn such that x of n is equal to 0 matrix. We can, because in the transformation we can say that kernel is nothing but is equal to is a 0 of V, here is a 0 of m by n m by 1 matrix is there. So we have a such a way means we can find the rank of this. If this is equal to we have a number of element in the basis of a rank number how many elements system of equation is there, then span of this again by this system of equation we solve and then find the span of a kernel of A. Number of element in the kernel of A is the basis is called the nullity of this thing. So okay, so nullity of A is the nullity of A is the dimension of the kernel of A is simply we can say that that's the kernel. What is the kernel of this is a clearly we can say that. Okay, so we just try to one example. Okay, this we can just say that we try to kernel of this means kernel of this means we can this can be written in the form of you have a 2 1 minus 1 2 3 0. Now we have a x y z. This can be written as in the form of you have a simply you have a sorry this is x y because we have a matrix is equal to 3 by 2. So this is equal to x and y. So this means we can say that this is nothing but is equal to you have a 2x plus y, then you have a minus x plus 2y. Now this is we can write ax can be written in this form to 2y and then you have a 3y, and now we have to just say that this means by the definition of if we find the kernel is nothing but a of x is equal to 0. So this implies that we can say that we have a 2x plus y, then you have a minus x plus 2y, then you have a is equal to we have a 0 0 0, and this can be right in the form of this clearly you have a 2x plus y is equal to 0. Now minus x plus 2y is equal to 0, then we have a 3y is equal to 0 means clearly y is equal to 0. If y is equal to 0 implies that x is equal to 0, then we can say that kernel of A is nothing but is equal to you have a only 0 matrix, so 0 by 1 matrix. So this means clearly is equal to 0, and then we can say that the dimension of A is clearly dimension of a sorry nullity of a dimension of a kernel of this, or we can say that nullity nullity of A is equal to 0. So this way we calculate into this form. Clearly this can be written into this form. So this is sorry this is 3x1. Okay, so this is not 0, this is 3x1. So simplify this, we can get in 2x1, so x1 is equal to 0, so x2 is equal to 0 and so on. So we can say that both the x1 x2 is equal to 0, therefore kernel of A is 0, therefore nullity of A is equal to we have a again 0 map. Okay, so now we try to this, so why find the this question. Okay, so this means we first we calculate the ax we have a 3 1 4 0 0 2 2 0 minus 1 minus 1 0 0, then we have a x1 x2 x3 x4, and then we have a this is nothing but is equal to you have a 3x1 plus x2 plus 4x3, then you have a 2 times of you have a x2 plus 2 times of you have x3 minus ka x1 minus ka x2, and this is matrix is this. Now we have again Ax is equal to 0, so you have a 3x1 plus x2 plus 4x3 is equal to 0, then you have a 2 of we have a 2 of x2 plus twice of x3 is equal to 0, minus of x1 and minus का twice x2 is equal to 0. So this implies that x2 is equal to minus का x3. This implies that you have x1 is equal to, you have minus का 2 times of x2. So this means x1 is equal to, you have a minus का this is equal to, you can say that is equal to twice of x3. Then we can say that kernel of A, span of the kernel of A is nothing but is equal to, we have the form of this, we have x1 is equal to, we have in the form of x3. So we have a twice x3 minus x3 and then we have x4 such that x3 and x4 are the any element of a real. So this means we can say that span is equal to, you have a 2 minus 1 1 0 and we have a 0 0 0 1. So these two vectors are linearly independent. In this case we can say that nullity of A is equal to, we have a 2. Okay, so now we just check as a nullity of this is equal to, we have a 2 clearly. So this means we simplify this. So this means we have to just say that into this form. So nullity of this is equal to, you have a 2. Now we know that already rank plus nullity is equal to dimension of a Rn or Vn. This theorem, which is true for a linear transformation between the finite dimensional vector spaces. It is also true for matrices because of the identification of the matrix as a linear transformation. We already know that. So we try to by this we can say that clearly a square matrix is non-singular if and only if its column vectors are linearly independent. So we just say that clearly. So first just is one example, we try to find the range, kernel, rank, nullity and try to verify this rank nullity theorem or not. So we just say first we calculate range of A. Range of A is nothing but is equal to, we can say that span of 1 1 minus 1 transpose 2 1 1 transpose 1 3 0 का transpose. So now these three vectors, now you check clearly 1 3 0 can be written as a, you have a 1 1 minus 1 plus 0 2 1 and now 1 plus 1 2 plus 1 3. So this means three vectors are clearly linearly independent. So R of A is written in the form of a span of, you have a 1 1 minus 1 ka transpose 0 2 1 ka transpose and then clearly these two vectors are linearly independent. So we can say that clearly rank of A is nothing but is equal to, you have a 2. So rank of A is equal to 2 and dimension of a Vn is equal to, we have a 3 Rn R3 because this map is R3 to R3. Now we take a of x, so we have to just say that we have a 1. I just take a x1 x2 x3 here, multiply this matrix, we can calculate Ax. So Ax is equal to, we have a x1 plus x3, we have a x1 plus twice x2 plus 3x3, then you have a minus x1 plus x2. Now we have to this, we know that by the nullity Ax is equal to 0 null space. So we have can say that simplify this, x1 plus x3 is equal to 0. Now we have x1 plus twice x2 plus 3x3 is equal to 0. Now minus x1 plus x2 is equal to 0. Then you have a clearly x1 is equal to, you have a x2 and x1 also you have a x1 plus x3. So we can say that simply is equal to, you have a x2 is equal to, you have a x1. Now x3 is equal to minus ka x1. So this means you have a x1 and then 2x. Okay. So this means kernel of A is nothing but equal to span of we have the element of all of the x1. So you have a x1, x2 is equal to x1 and then minus ka x1 form. This such that x1 is the element of a R although this can be written as a span of, you have a 1 1 minus 1, and this is a non-zero vector, is a linearly independent, then clearly we can say that the nullity of A is equal to 1, and by the rank plus nullity. So, you know that the rank of A plus nullity of A is equal to, we can say that this implies that rank is equal to, we calculated 2 plus nullity is equal to 1, then is equal to 3. This is the same as a dimension of r to the power 3. So, this means we can say that clearly we have to show that if we have a matrix is given, then by the matrix is given we can find the rank and nullity, and then also satisfy this theorem. For a rank nullity theorem is also applicable in the case of a matrices also. Okay, so now this is all I just how to calculate the rank and nullity, and if we have to calculate the just nullity, then by the here I just use the theorem, rank nullity theorem. For this me I just using this in the form of this rank of A plus nullity of A is equal to, you have a 3. So, nullity of A already calculating is 1. So, we have a rank of A is equal to, you have a 3 minus nullity of A, then you have a 3 minus 1 is equal to 2. So, we have a rank of A is equal to, we have a 2. So, we have already proved both the side. I just calculating the rank of this also, and then we have to this. So, this is the clearly I just said that other way I just show you this. This means clearly we have a this is a singular matrix, because rank is because you know that if you show that is a non-singular case, means a linearly independent vectors is not a these vectors are not, all the 3 vectors are not linearly independent, they are dependent. So, this is a dependent, means this can be said that is a non-singular, is not a non-singular, is a singular matrix. And also you know that the for a singular case, you know that the kernel of a, if we have a linear transformation is equal to 0, then we can say that if kernel of a transformation is equal to 0, then we can say that T is equal to 1 1. Here is also the same thing is here. If kernel of A is equal to 0, then this A is a matrix is a 1 1, and also we know that the dimension of a V is the same as the dimension of a W. Then we can say that if T is a 1 1, then A is also is a onto. So, this is A is, we can say that this is, we can say that this is equal to, we have a is implies that A is onto, or this is true for both. So, if we have both the vector spaces dimensions, here is we have a this matrix from A is R3 to R3. So, this means we can say clearly this is a singular matrix, is not a non-singular matrix. This is not a non-singular, this is a singular matrix, we can say that. Okay, one more example we try, and then just if it time permit, we can discuss 1 or 2 more examples, and then we move to the some other topic. Okay, so this again we have to take a R of A is nothing but is equal to, we take a span of the column of this vector. You have a 2 1 1 ka transpose, you have a 1 2 1 ka transpose, you have a minus 1 0 minus 1 ka transpose. Now, if you check is these 3 vectors are linearly independent or not, then you just say that we just check is this 2 vectors are linearly independent or not. So, because these 3 vectors are a span of these 3 vectors. Now, check if these 3 vectors are linearly independent, then we can say that this is true. So, rank of A is equal to 3, because these 3 vectors are linearly independent, because none of them can be written as a linear combination of other 2 vectors. So, this means we can say that clearly these vectors are is a non clearly is a rank is equal to 3, and because this is equal to 3 by 3 by the rank nullity theorem, rank of A plus nullity of A is equal to 3. So, rank of A is equal to 3 plus nullity of A is equal to 3. This means nullity of A is equal to 0. So, if nullity of A is equal to 0 means we can say that clearly if T is 1 1 and onto, then this is A is 1 1 and 2 is a non-singular, And now we can try to solve this. The kernel of this is equal to verify the kernel of this also is in the form of 0. So we take a AX form. So you have a AX can be written in the form of you have a twice x1 plus x2 minus x3, and then we have another term, you have a x1 plus twice x2, then you have a x1 plus x2 minus x3. This is the matrix. Now we can say that 2x1 plus x2 minus x3 is equal to 0. Then you have a x1 plus twice x2 is equal to 0. Now you have x1 plus x2 minus x3 is equal to 0. So if we have to adding and these two, simplify these two equations, you can just say that here you can say that x1 can be written in the form of minus twice x2. So this means we can say that is equal to minus twice x2, and plus you have a this is equal to x2 minus x3 is equal to 0. So we have to just say that we have to minus x2 and minus x3 is equal to 0, and then by this we have a x1 2x1 plus x2 plus x3 is equal to 0. So this means we can say that x1 is equal to you have a x3, and then we have x3 x1 is x1 x3 are the same. So this means this is cancel out. So you have to getting this x1 is equal to 0, and then you have x2 is equal to 0, then x3 is equal to 0. Then we have say that kernel of A is nothing but is equal to 0. So this means we can say that clearly this is 0 subspace, means this is a nullity of this set is equal to 0. Okay, now we have a find the range kernel rank of all this thing. So I start with the first one. So which is range of A for this one. For example, this is A. Is the form of a, we have to just say that span of, we have a 1 minus 1 1 ka transpose, now we have 3 7 0 ka transpose, now a 2 2 1 ka transpose. And now you just check these three vectors are clearly is a linearly independent, because we cannot write any one of them with linear combination of as any two. So that's means these three vectors are linearly independent. So we can say that rank of A is equal to, we can say the range of A, this is the same, and then now we can say that rank of A is equal to you have a 3. Then by the rank nullity theorem we can say that the nullity is equal to. So now let us try to verify this. We have a we can write A of x for this is equal to, we have a, this is a matrix, we can say that we have x1 plus we have a 3 x2 plus twice x3. Now we have a minus x1 plus 7 x2 plus twice x3. Now you have a x1 minus x3, and this is equal to, you have a 0 0 0. Then you can say that clearly x1 plus 3x2 plus twice x3 is equal to 0. Now you have a minus x1 plus 7x2 plus twice x3 is equal to 0. Now you have x1 is equal to, you have a x3. Now you have x3, we have to substitute here. So you have a 3x2 plus 3x3 is equal to 0. x1 substitute is x3. So you have a simply is equal to 7x2, and then plus you have a x3 is equal to 0. So this is 3 3 is cancelled. So you have a x2 plus x3 is equal to 0. 7x2 plus x3 is equal to 0. Now we have subtracted this is cancel out. So you have a minus 6 x2 is equal to 0, and you have a minus 6 x2 is equal to 0, implies that x2 is equal to 0. If x2 is equal to 0, then we can say that clearly from any one of the equation we have to x3 is equal to 0, then we have a x1 is equal to 0. So this means we can say that kernel of A is nothing but is equal to 0 subspace, and that means this matrix is given is a non-similar matrix. And now we can verify this because it's equal to 3. So we can say that rank of A is equal to 3. So 3 plus kernel of A, this is equal to 0 is equal to 3 is also satisfy this for this thing. I just try for the second one is equal to 1 minus 1 2. So I just take write a matrix here. A is equal to, you have a 1 minus 1 2, 1 minus 1 2, 3 minus 2 5, and then 3 minus 2 5. then clearly range of A, if we can write as a column vector of this, we can say that clearly we have a span of, we have a 1 3 ka transpose, -1 -2 ka transpose, 2 or 5 ka transpose. Now clearly you see this 2 5 can be written as a 1 times 1 3 plus -1 times 1 2. So this is equal to 2, and 5 can be written as a this linear combination of these two vectors. This means these three vectors are linearly dependent. So we can say that A is equal to nothing but is equal to span of, you have a 1 comma 3 ka transpose, and you have a -1 -2 ka transpose, and now one of them is not a scalar multiple of other. So we can say that these two vectors are linearly independent. If these two vectors are linearly independent, then we can say that rank of A is equal to, you have a 2, and clearly by the rank nullity theorem we can say that the nullity of A is equal to, you have a maybe is equal to 4 minus 2 is equal to 2. So we just check, verify what is the nullity of here by this. So we can say that A of x is equal to 0. So A of x is the form of a, you have a 1 -1 2 3 minus 2 5. Now we have a x1 x2 x3, and then we can say that this is nothing but is equal to 0 0 0. So this can be written in the form of a, we just say that satisfy this. You have a x1 minus ka x2 plus ka twice x3 is equal to 0. Then you have a 3x1 minus ka 2x2 plus ka 5x3 is equal to 0. Clearly we have a 3 variables and 2 system of equation. There is infinitely many solution is exist here. So we can just say that clearly, you can say that we can say that x1 or x2, any one of them can be written as a so just take a x2, we just take a x2 can be written as a x1 plus twice x3, and so we can set that, substitute here x2 key value here, then we can get a, so this means x2 can be written in the form of a linear combination of the x1 and x3. So this means kernel of T can be written as kernel of A can be written as a span of, you have a x1, and now you have a x1 plus twice x3, and you have a x3, and then this can be written as a span of, you have a 1 1 0, and you have a 0 2 1, and these two vectors are clearly linear independent. Then we can say that nullity of A is equal to, you have a 2, and then you can see clearly you have a rank of A plus nullity of A is equal to dimension of A, this is equal to 4. So you have a 2 plus 2 is equal to 4. So this completes the solution of this problem. Okay, so this one I just leave this for your home assignment, and similar problem you can solve also. So now I just stop today's class at this point, and in the we know that in this class we discuss about the rank, kernel, and nullity of a linear transformation, because in the previous classes we already show that matrix represents as a linear transformation. Similar fashion. Okay, so now I stop this. In the next class we continue some new topic. New topic is how to solve a system of equations. We discuss the system of equation in the next class. Okay, thank you very much.